Hello, Assalamu alaikum, everyone. I welcome everybody to the workshop on numerical jointly organized by IEEE EDS Buet Student Branch Chapter, IEEE EDS Bangladesh Chapter, and Solid State Circuit Society. The workshop will be instructed by Dr. Ahsan ul Alam sir, who is a Senior Research and Development Engineer at Ansys Canada Limited. He completed his PhD in Solid State Electronics from the University of Alberta. His expertise is on simulation of active photonic devices and developing compact model for photonic integrated circuit simulation. So it will be a great opportunity for us to learn a software from such an expert. We would like to give special thanks to Dr. Hassan Alum sir for managing time in midst of his busy schedule. The success of this workshop still depends on us, the participants. How well we learn from it and how well you interact with the instructor will determine the accomplishment of this workshop. So if you have any questions during the workshop, please raise hands and we will give you the floor. And I also request everyone to rename their ID according to their name. Now, without wasting any of your valuable time, we may start the session with the permission of Dr. Hassan Alum sir. Sir.
Oh, yeah. Can everyone hear me? Thanks, Amit.
Yes, sir.
Okay, yeah, I'm unmuted, so I hope everyone can hear me. Yeah, thank you so much for organizing this. And yeah, I'm so glad to be joining everyone. And I'll try to show some of the features of the tools that we're going to see today. And hopefully that helps everyone. Let me share my screen and get to our slides for today. Okay, so maybe before we start, I'll first just apologize from beforehand that I think like most of us, I'm working from home as well. So, and it's a holiday here today, early in the morning. So everybody's asleep, but they'll soon wake up and the kids will come downstairs and maybe make some noises. So sorry about that. So hope everyone can see my slides. So again, another apology is that it's been a while since I have used Fdtd mode and these tools. As Samit mentioned, my work focus is primarily active components in photonic integrated circuits. So these days I work mostly with the things that we are going to talk about in day 2, which is charge, heat, and interconnect. So these are our electrical and thermal solvers, more kind of like along the line that I have been working on for a while. And then interconnect is the circuit, photonic circuit simulator. So that's something that I work with a lot as well. So on day 2, I'll probably be more comfortable in doing this presentation and talking about the tools. Of course, like as I've worked with a lot of different people over the years, I have had some exposure to Fdtd and mode, which are our pure photonic solvers. And so I'll like give it a try to share kind of like some of the features of these tools and show you some examples, and hopefully that'll help everyone. If there are any questions, yeah, please feel free to ask and I'll try my best to answer. So without further ado, let me go through the slides. So the first slide is just to introduce kind of like all the set of tools that are part of the Ansys Lumerical software set. So we break down our tools into these 3 parts, as you can see. The top part is about photonic integrated circuit simulation. So as you know, photonics is a huge Zoom notification that failed to connect cloud server. I hope I'm still connected though.
Yes, sir, it's okay.
Okay, thanks. Okay, I don't know why that showed up. Okay. So on the top part, you can see the photonic integrated circuit simulation set. So as I mentioned, interconnect is the circuit photonic integrated circuit solver. So the screenshot here, you can see a schematic of a photonic integrated circuit with lots of different components. And if you have a system like this and you're trying to simulate like a very big combination of different tools that build a big circuit, that's the tool that you're going to use. It also supports our Photonic Verilog A platform. So when you're simulating a large photonic integrated circuit, usually you build a compact model for your individual elements. You build the circuit and run simulations, kind of like what you do in SPICE simulators for electrical components. So in SPICE simulators, when you simulate electrical circuit components, one option to define the behavior of the different elements is by using Verilog A, which is a programming language specifically designed for this purpose. Since the majority of the electronics community are very well versed in Verilog A, there is a big motivation in simulating photonic circuits using Verilog A as well. And so as part of the product offering of Ansys Lumerical, there is also a set of photonic Verilog A models available to users. And so this particular product talks about that. So just like you can run photonic simulations in interconnect using the Photonic Verilog A platform, you can actually run photonic simulation of different photonic elements in Cadence tools or any SPICE tools where they support Verilog A based models. CML compiler here is another product that goes in this category. And this one is used to generate the compact models that interconnect uses. So if you have a Y branch and you know how it behaves, you can, the first thing that you have to do is you create a compact model, just like electronics. You create a photonic compact model, and then you put that in interconnect in your circuit to run simulations. So that's something that CML compiler can help with. Now going down to the photonic multiphysics simulation bundle here. These are the tools that we will mostly be talking about. So we have Fdtd and Mode up here. These are our optical solvers. And then we have Charge, which is the electrical solver. It's used to simulate electrical transport in semiconductor-based devices. Then we have Heat, which performs thermal simulation in solids. So the devices that you simulate with Charge, let's say, you can also see their thermal behavior. These two solvers can be combined together, and you can do electro-optical co-simulation. So that, let's say you have PN junction diode, you're applying a lot of voltage to it, lots of current flows, and it heats up. And you want to see how getting heated up affects the behavior of the device. In that case, you can use Charge and Heat together, and then see how the electrical behavior changes as the device heats up. 𝗂𝐄𝐄𝐿 is a new solver. It performs quantum mechanical simulation of quantum wells, and the primary use is to figure out the gain profile of 3-5 based material systems. So you can use it to simulate lasers or SOAs and electroabsorption modulators and so on. Dztd is another 3D electromagnetic solver. It's similar to Fdtd. The primary difference is that Fdtd uses finite difference time domain approach. So you use a rectilinear grid to break down your simulation volume in Fdtd, whereas Dztd uses a finite element based approach. So it has certain advantages over Fdtd, where if you have a very complex geometry, you are able to resolve it with less extensive mesh. And Dztd uses a discrete Galerkin time domain method, which allows you to have discontinuity in electric fields in your simulation. So it's pretty well suited when you are dealing with plasmonics. Of course, Fdtd is the industry standard when it comes to electromagnetic simulation, and it's the more matured tool. So if you're doing optical simulation of any devices, most of the times you'll probably be using Fdtd. There are some scenarios where you may want to switch to Dztd given the complex geometry of your device, or maybe you have you're interested in plasmonics and you need a very high accuracy. And then maybe in that case, Dztd will be advantageous. Theme is another optical solver. It uses an Eigenmode solver to solve optical modes in waveguides and optical fibers. It also uses a finite element approach. So the same calculations can be done using mode, which uses a finite difference approach. And so theme is kind of like the finite element counterpart of that. And it has like the similar advantages like Dztd, that you can use a finite element mesh. And so that allows you to resolve complex geometries more easily compared to a finite difference mesh. The last one is stack. It's an analytical solver, and it's used, as the name suggests, it can be used to simulate multi-layered stacks of elements. And this is a very quick way to design multi-layer stacks and figure out how light goes through or gets reflected from these layers. On the right side, we have miscellaneous set of capabilities that can be combined with any of these tools. So any of these softwares can be used in cloud, AWS, Microsoft Azure, and so on. They come with automation APIs, so you can combine them with MATLAB or Python, and all the tools have also their own scripting language, the Lumerical script. So you can script everything and make things automated. That's supported by all of the tools. And also they combine with third-party tools like 𝗵𝗘𝗘𝗘𝗘, Scale-Out, MATLAB, and so on. When you're thinking about photonic integrated circuits, if you're interested about how these tools work with different foundries, so here's a list of different foundries that we have worked on. And so either we have compact model libraries with them that you can run in interconnect, or there are process files from these foundries that you can get, and you can build your design in Fdtd or in mode, and then design your circuit components by using their process file, so that the final geometry that you get is going to be very accurate according to the foundry process. So that was kind of like a brief introduction of our tools, just to let everyone know kind of like what are the different parts that are available, so that if you need any one of them, you know that it's there. So for today, let's see. So we're going to focus on Fdtd first. So as I mentioned, Fdtd is our optical solver. It's a fully vectorial 2D, 3D Maxwell solver. So it basically solves Maxwell's equation in 2D or 3D space. And it uses a finite difference time domain method. So that means that you discretize your whole simulation region in rectilinear grids, either in 2D or 3D. And then as light propagates through your simulation volume, you calculate how light goes from one grid point to another as a function of time. It's a very well accepted industry proven approach, and most of the commercial photonic solvers uses Fdtd. The tool that we are going to see today is the industry leader in this category. So hopefully when you use it, the nice thing would be that you can rely on the accuracy of the solver, and you can depend on the results that you get. Here are some applications of Fdtd. So as I was mentioning, photonic integrated circuits, there are lots of different parts that goes in a circuit. And so you can obviously simulate those different parts using Fdtd. Cmos image sensor, the optical part of the image sensors can be simulated, solar cells, OLEDs, effects of nanoparticles and plasmonics in any device, liquid crystals, photonic crystals, gratings, photolithography, metamaterials, and defect detection. So these are some of the examples, simulations that you can do with Fdtd. Given the time, we will probably look at like very few examples today, but there are application examples available on our website. So you can just create an account on Lumerical or Ansys website, and then you'll have access to these examples. So you can download them. When we go into the demo, I'll show you how to access the application gallery and download examples. Okay, so maybe just some small discussion about what Fdtd does and how it compares to, say, the more conventional way of doing kind of like figuring out how light moves, which is by ray tracing, right? So I think ray tracing is something that probably everyone is familiar with. Even when we're studying in high school, like we studied like how light goes through lenses and how light can converge or diverge depending on the type of lenses that we're using. And so ray tracing is just that, and it can be used to figure out like how light interacts with different structures and objects and how it moves. So what is the difference between ray tracing and what Fdtd does? So the main difference is that when light moves and interacts with different elements, depending on the size of those elements, the behavior of the light can be different. So you may be able to use ray tracing to figure out how light would interact with something if it's much bigger than the size of the wavelength of the light. However, if the feature size on that structure, so the structure itself can be big, but maybe it has like very tiny particles on top that have sizes comparable to the wavelength. And in that case, you need wave optics. You cannot use ray tracing. And so that's when you need tools like Fdtd. So here is an example. This is an Cmos image sensor. So you can see that we are assuming that the light that comes into the image sensor has a wavelength of 0.55 micron. And you can see here we have a 4 micron by 4 micron block, and you can see there are feature sizes that are much smaller. These are the lenses that collect the light and puts them into the core of the sensor. And so in such simulations, you can imagine that using ray tracing is not going to be accurate. And I believe there is a slide here. So when you're doing ray tracing and you're trying to figure out like how light goes through, say, a set of lenses, you use Snell's law, right? So you know the index of the two different layers, and then you figure out like if light is incident in a certain angle, like how it reflects or if it refracts. It's all given by Snell's law. Right, so here, I guess we are getting total internal reflection depending on the index of the two layers, and then you might get a total internal reflection if light is incident on 45 degrees. So now in such a case, if we now perform a simulation with two different wavelengths, so let's see what happens. On the left side, I believe here we have a wavelength of 0.4 micron. So the wavelength here is much smaller than the feature size. And so you can imagine that ray tracing would actually work. So let's run this video. So the simulation is done with Fdtd, but it will kind of show you that the concept of ray tracing is valid given that the wavelength is much smaller than the structure. And you can see that light came from the top. You had total internal reflection from these two surfaces, and then the light goes back up, right? So something that you can actually figure out with ray tracing. Now on the right-hand side, the wavelength is increased, right? So now the wavelength is comparable to the geometry that you have. And so now you can see that what's happening here is much more complex. It cannot be described by ray tracing. And that's because as light comes and reflects from the two surfaces here, you get interference patterns happening because the light from the two surfaces are overlapping with each other, and you get behavior that cannot be expressed or explained using ray tracing. And then that's when you need to use a tool like Fdtd. Okay. So as I mentioned a little earlier, Fdtd uses a time domain based technique. So when you run your simulations, you are solving for the electric and magnetic field in your simulation area as a function of time. Now, when you're looking at a photonic simulation, you usually want, usually talk about the optical spectrum, right? So you want the electric or magnetic field as a function of wavelength or a function of frequency. So what we do is after you run your simulation and you have your electric field as a function of time, you can simply do a Fourier transform, and then that gives you the optical spectrum or your electric field as a function of frequency or wavelength. And so as you know that for any system, if you want to calculate the impulse response of your system, you divide your frequency response with the source spectrum. And so in Fdtd simulations, by default, when you run your simulation, in the end, you can get the frequency domain spectrum of your electric field, and then you divide that with your source power or source spectrum to figure out the impulse response of your whole system. And so if you have a particular device and you want to see how light is getting transmitted through it, what you want to see is the spectrum of transmission, like at each wavelength, what fraction of the light is getting through and what fraction is getting reflected. And so this is how you can obtain the impulse response of your whole system. And this is done by default. So when you're using a monitor to see the spectrum, as we will see later on, these calculations are done internally. So here is an example. Here we have a simple empty space, and then we have a plane wave going through. And so as you run the simulation, you will see that it's a time domain solver. So light goes through the whole system, enters from one side where the source is located and leaves through the other side. And so let's say that's our source. So it's a pulse that got injected in our simulation, and it has a certain spectrum. And then on the other end, if you look at the electric field, you'll see that the source propagates and goes through the empty space on the other side. And then that's the spectrum of the output. And then now, in order to get the impulse response of your empty space, you simply divide the output electric field spectrum and normalize it by the source spectrum. And the result would be 1 because it's an empty space, right? So if you figure out what is the transmission at every wavelength, the probability of transmission is 1. And so that's how the calculation works. Of course, when you have a complex system, these spectrums are going to be very different from each other, and then you will figure out like what your transmission spectrum looks like from the simulation. So here is a more complicated example. Here we have a ring resonator. You have 2 optical buses on 2 sides. As light comes through the top bus, it couples to the ring depending on the wavelength. And then some of the light couples through the ring, and then it couples to the bottom bus here. And then as light goes through the cavity, it slowly couples to the two buses, and then the light leaks out, and then eventually the intensity in your ring goes down. So the way the time domain simulation works is that it keeps track of the total amount of light in your simulation area or simulation volume. And then the simulation runs until all the light has gone out of your system. And once kind of like all the light goes out of your system, then you take your time domain electric field response, and then you do a Fourier transform to figure out what was the spectrum at each, what was the spectrum of the electric field. So the way the ring works, as I mentioned, if you inject a light of different frequencies on this waveguide, only at certain frequencies, the light from the waveguide couples with the ring here. And that depends on the group index of the ring and the radius of the ring. So at particular wavelengths, light would simply go through and not couple with the ring here. But at other wavelengths, it will couple to the ring, and then you'll see light entering here. So if you perform an Fourier transform of the electric field that we just saw as a function of time, and then you look at the spectrum at different wavelength. For example, for some wavelengths where there is no coupling, you'll see that the light just goes through and it doesn't interact with the with the ring here. But at other wavelengths, you will see that the light strongly couples with the ring, and you see high electric field on the ring itself. So that's kind of like how the simulation works. You run your simulation in time domain, but then the useful information that you are after, you get that by doing a Fourier transform in the end. So here are some key features of Fdtd. Usually when you're running simulations of an optical system, the simulation can be really large. So the Fdtd engine is fully parallelized. So you can break down your simulation between multiple machines if you need to, and then run your simulation in a reasonable amount of time. In terms of material modeling, Fdtd has lots of built-in material models for common materials, so you can utilize those. It also allows you to bring in material data from elsewhere. So if you're working with something that is not in the material database already, you can bring those informations from elsewhere. In terms of meshing, Fdtd uses a rectilinear grid mesh. So you can imagine that if you have a complex geometry, defining that or resolving that with a rectilinear mesh can lead to error. However, it uses conformal mesh technology where it actually can very accurately resolve curved surfaces and complex surfaces as well. So even if you have a complex structure, you can use Fdtd and get accurate results. Electromagnetic Toolbox, so it has lots of analysis tools that you can use for post-processing. We will see, I believe, at least one of them today. And then here are some of the common features that I already talked about. One of them maybe we will also see is parameter sweep and optimization framework. So when you're designing something, you start with an initial design maybe, and then you try to improve it. And so that's when you can do either parameter sweep. So you parameterize your structure, which you can do in Fdtd mode or charge and theme. And then you can sweep those parameters and then see how the behavior of your element changes. And that there are optimization tools also that can allow you to optimize your design in a more automated way. So yeah, let's skip these ones. We already talked about some of them. So the first example that I thought of showing is an anti-reflective coating. So this is a very simple structure and simulation. So it's good to get started and just get a feel as to how the tool looks like and where all the simulation objects are. So I'll just quickly go through the example and show you all the pieces here. Right, okay. So I hope everyone can still see my screen here. I'm just gonna make this window slightly bigger. Okay, so let's look at the XY cross section here. As you can see, when you open up Dft, you have all of these 2D views of the different side views of your device, and then you have this 3D perspective view as well, where you can actually see the whole design in 3D. However, I myself find this 2D view much more useful, especially if you're running simulations in 2D. So the way the tool is organized, you'll see that there are there are toolbars at the top that shows all the different simulation objects that you can add. We will take a look at the different simulation objects very shortly, so I'm not going to go into much details now. On the left side, we have the objects tree. So this shows you the things that are actually getting used in this particular simulation. So Fdtd here, this orange rectangle is your simulation region. So we're doing a 2D simulation here, and you can see on the XY plane, so that's your simulation region. It's a small rectangle. The source is a plane wave source. So light will go from the top towards the bottom to your structure. And then in your anti-reflective structure, you have a silicon substrate here, the large rectangle at the bottom. And then we have an anti-reflective coating on top. If we go into these rectangles, you will see that these are just rectangles or geometries that you can define the dimensions here to give them the exact size that you need in your device. And then there's a materials tab where you can fill it up with any material that you want to. So you can either pick a dielectric and then define the index of your dielectric for the simulation, or in the drop down, you can easily see all the materials that are available in the material database. So you can scroll through the database and then pick whatever material you want to use in that particular layer as well. So the material database can also be accessed from up here. And if you go in, you'll see that all the material definitions that are already part of Fdtd are here. And you can see there's an add button. So you can add more materials to the database if you have the data available for those materials. Now we have our source, we have our geometry, and then the other thing that we need are called monitors. So these monitors collect the electric or magnetic field in your simulation, and then they give you the results that you want. So here we have two Dft monitors. So these are frequency spectrum monitors. And I believe we have just line monitors here because we are doing a 2D simulation. So we only need to capture the electric field, say, above the structure to see how much of the light is getting reflected. And then we have another monitor. Let's click on this one down here to see how much of the light will go through this anti-reflective coating. So two monitors, one to capture the reflection of light, one to capture the transmission. And that's the simulation setup. So as I mentioned, it's a simple setup. And so if I click run, what will happen is we will inject a plane wave light from the top directed towards the geometry here. Light will go down. Some of it will get reflected by this coating, but some of it will also pass through the coating and go into the silicon layer. And then these two monitors will tell us how much of the light got reflected and how much of it went through. And then we can decide like how good of a coating is this. And then we can optimize the thickness of this anti-reflective coating layer to make sure that it is blocking the light as much as we want. So once you have things set up and you have your simulation region, you have the material filled up everywhere, you can simply click to run the simulation. This is a very small one, so it runs very quickly. And once the simulation runs, you can see the icon changes here. So that tells you that you have results available. So this is the monitor that we were using to figure out how much of the light is getting reflected. So right click and visualize the electric field, let's say. And so we can see that about 12% of the light is getting reflected. Okay, and then, okay, it's a single frequency simulation. And so this is the x-axis here. So you can see that it's a plane wave coming through. So obviously at every point, you just get the same reflection going upwards. And then now if we plot transmission, maybe on the same visualizer. So you can either plot it in a different visualizer or on the same visualizer. So I'll just plot it on the same one so that it's easier to see. And then so now the new line is the green one. So you can see that some of the light is getting reflected, and then other part of it is getting transmitted into the silicon layer. So yeah, obviously this is not a very good design, right? A lot of the light is still getting reflected. So what you can now do is you can do a sweep, as I mentioned, to optimize your anti-reflective coating. So we're using a parameter sweep, and then in the parameter sweep, you can choose any property of your design here, and then change its value as you run multiple simulations. So here you can see we are creating a parameter called thickness, and then in the drop-down menu, you can pick the thickness of the anti-reflective coating, and then you can change the thickness from say 0 to 0.15 micron. And then in terms of result, you're collecting the reflection and the transmission from these two monitors. And I'm not going to run the simulation now to save time, but looking at the icon, you can see that this sweep was already run, and then it has some results. So let's just look at the results. So now you can see here in this plot that as we varied the thickness of the anti-reflective coating, and we're looking at how much of the light is getting reflected, because we're looking at the result from the R monitor here. You can see that without any coating, a lot of the light is getting reflected here. But as you change the thickness at a certain value, you can see almost no light is getting reflected. And then again, beyond that thickness, again, you get some light reflection, and it goes on and on. So by doing a sweep like this, you can figure out that, okay, if I make my thickness 0.06 micron, I believe this is micron, right? Yeah, this is in meter. So 6 × 10⁻⁸ means 0.06 micron. So if I make my thickness 0.06 micron, you get a reflection of 0.001. So that's 0.1% of the light getting reflected. And so that way, if you want to put an anti-reflective coating on top of your silicon, you need to put a 0.06 micron thick layer of anti-reflective material with a dielectric index of 2. And then for more complicated system, when you have lots of different parameters that you need to juggle with, often a parameter sweep is inconvenient. And then there are tools for optimization. So here, I'll just open this one up just to show what's available. So in the optimization algorithm, again, kind of like you can define the parameters that you want to change to optimize your design. So in this parameter window, you can add parameters, and then you can look at different objects. So for example, if you want to change the, the thickness of the anti-reflective coating, again, just to show you how you pick that, you can go through all the elements in the object library, object tree here, and then select them, and then pick any property of those objects that you want to vary. So here, I guess like the thickness of the anti-reflective layer would be the Z span. So you can pick the Z span and then you can change it. So you can say that it's a length. So it has a unit of microns. And then when you're optimizing, you can say that like, okay, when I'm optimizing, I can go between a length of 0 to 0.5 micron or something like that. And then you can have multiple parameters here listed for different geometries. And then you can collect the results that you want to collect. So we call here, they're called figure of merit. So things that are trying to optimize. And then you can select whether you're trying to optimize them. So for example, here we are trying to optimize the reflection. So you select the reflection here, and then you select to optimize. And then so that says that, yes, you're trying to optimize this. You can also collect other results that you're not trying to optimize, but still it'll collect those results so that once you have your optimized design, maybe you want to see that, okay, that's the reflection, but how much is the transmission through the layer? So you can collect like additional results along with it as you run the simulations. So those are kind of like the different tools, and gives you an idea as to how you set up a simulation and run it and collect some results. So hopefully that was a simple enough first example to take a look. I'll just close it now and then go back to our slides. Okay, so I believe these were just, yeah, these slides just talked about. So usually how these workshops work, unfortunately, is that people would, everyone would have a copy of the simulation files. And then as I do my presentations, you would open up your file and then you would actually go through the file and run simulations. However, yeah, I guess like given the situation that we are all in right now, unless you have two monitors, it's not possible to take a look at my presentation and then run simulations on your side at the same time. So I didn't think it makes sense to do things that way anymore, unfortunately. So for the workshop, I'm going to open up simulation files and show you. And then in the end, I'll share those files with the organizers so that they can maybe distribute those files with you, maybe put them somewhere so that you can all download it. So we can work that way. So let me see. I think, yeah, these slides were all about the anti-reflection coating. So that's that. Let me switch the slides now. Okay, so going forward, maybe we can learn a little bit more about the Fdtd design environment. So I have some slides that will introduce all the different simulation objects. Some of them you already saw a little bit, and then there are others that we haven't seen. So I'll talk about those. So in terms of the simulation objects that goes in an Fdtd simulation, obviously there are structures to create your geometry. There are attributes that you can use to import some data on top of your geometry. We will see a list of them soon. There are different groups, so they can be either structure groups to create that help you create complex geometries, or analysis groups that allows you to run some post-processing on your simulation results. Solver regions. So in the simulation solver region, you need to apply lots of different boundary conditions, and we will talk about them. Ports also for injecting light and collecting the output. Different sources for different types of simulations. We will talk about them, and then different monitors to collect different kind of results. So the first step is structures, because you have to create your geometry in your simulation region. So in the Fdtd area environment, you'll see there's a structures button, and then it's a drop down button, and you can see lots of different shapes available underneath it. The most common one, of course, is the rectangle that we used, but you have triangles, polygons, circles. So using these, you can create complex geometries. And so if you have a very complicated geometry, you can imagine that you would use multiple elements from the list, and then together combined, they will create your complex structure. You can also import your design from GDS files, for example. So GDS2 is a very popular format that represents information about a 2D layer, and it's very common to use these type of files when you're dealing with photonic integrated circuits. So if you have a circuit and you have circuit components, most of the times you'll have GDS2 files that define how the layer looks like in a foundry process, and you can import those layers in your simulation and create 3D geometries out of it. Okay, so if you start to hear noise in my background, again, my apologies. People are waking up here, so there will be some noises in the background. There are other elements. So here, using this particular surfaces element, you can import pictures from AFM, atomic force microscopic, where it gives you a picture of how a surface looks like, and from that you can actually you can create a 3D geometry. NK materials. So this is when you have a very complex design where not only your geometry changes, but the index changes as a function of position. So using this import object, you can actually import the N and K value, which is the real and imaginary part of refractive index at different locations as a data, and then the geometry will get created based on the data. Binary import allows you to import a simple one-ends combination of binary data that defines the structure. And then images, you can actually import a simple image, and depending on the gradient of color or in your picture, you can convert them into thickness, and then you can end up with a 3D geometry. It's pretty cool, actually. If you have when you're using the tool, you can try to import an image and then see how it works. So these are just some examples as to how complicated designs you can make, and how structures look like once you have imported them into Fdtd. So here we have some layers with I guess some impression on the top surfaces. This is, I believe, an example of an NK import. So you imported a rectangle, but from the color variations, you can see that the index is changing at different points. So the index of the material is a function of position here. This is an example where we imported a 3D design from a CAD tool. And then you can see that the rounded edges of your 3D geometry, and then they can be imported into Fdtd. This one is an example of a photonic integrated circuit. So you can you have like two grading couplers here, waveguides connected to the grading couplers, and then you have racetrack or ring resonators connected to it. So this one, I believe, like the layer information was in a GDS file, and then once you imported the GDS file, you get the 3D geometry in Fdtd. Right. So again, like as I mentioned, like this one is a surface import. So you get the impression on the surfaces, and then you import it into Fdtd, and you get a 3D geometry out of it. Okay, so next up is attributes. So attributes are something that gets added on top of your geometry, and you can kind of like tweak the behavior of the material in your geometry using these attributes. So the first one is an index perturbation or NP density and temperature attribute. So this is a very popular one if you're running simulations for active devices. So I believe like some of you are interested in active device simulations. For example, if you're simulating an optical modulator, and maybe you have a PN junction inside your optical modulator. As you apply voltage, the PN junction, you're putting it in reverse bias, so the depletion region is getting bigger and bigger, and then that means that you are taking charge away from your device, from the depletion region, like you're taking electrons and holes out of it. And so in an optical material, if you have a lot of free carriers, free electrons and holes moving around, they interact with the light as the light flows, and then introduces optical loss. But as you take the free carriers out of your material, then that loss goes down, right? And then the presence of the free carriers also change the effective index or the refractive index of your material. So it changes how light propagates through your device, how the phase changes, and so on. So you can imagine that simply by having a PN junction and applying a voltage, you can change the optical properties of a material, which is how people design optical modulators. And so if you want to simulate such a device, you need to somehow introduce the effect of the electron hole density into Fdtd. The same perturbation object is available in mode as well. We will see soon. And so the NP density and temperature index perturbation attribute allows you to import a charge density information from, say, our electrical solver. And then you can put that on top of your, say, silicon layer in Fdtd. And that allows you to include the effect of the charge density into your optical simulation. Similarly, you can import a temperature profile from a thermal simulation into your Fdtd, and then you can see how the index of your design material changes as the temperature varies, maybe from one region to another. So that's kind of like the use of the index perturbation attribute. The permittivity rotation attribute allows you to apply and, so for example, capture the effect of an electric field, and then maybe you have a ferroelectric material. So as you apply an electric field, the I guess the dipoles inside your material rotates, and then you can capture that effect. LC orientation allows you to simulate liquid crystals. Again, maybe as you apply a voltage in your liquid crystal and you orient the dipoles inside your material, that's something that you can model using the liquid crystal orientation. The matrix transform attribute also allows you to move, I guess, orient the dielectric tensors inside your materials. So again, this is an example of the index perturbation. Oops, sorry. Index perturbation or NP density and temperature grid attribute. So as I mentioned, you can bring in charge density information or thermal map from charge and heat. And then there is a material called index perturbation material. So you have to, in the material database, you have to define that when you have electron and holes in your simulation that you have imported, how is the index going to vary for your silicon layer, let's say. So you have to define a particular material type in your simulation and then use that material to fill up, let's say, the waveguide here. And then when you import a charge density profile from your thermal electrical simulation, the optical simulation will see the behavior of the material here change as a function of N and P density. So this is an example of, let's see, the top bar is hiding here. Oops. Anisotropic materials. So yeah, as I mentioned, these are some examples for the liquid crystal rotation, permittivity rotation, and matrix transformation, the other three grid attributes. So here, I believe you can see that how the dielectric tensors can rotate in space. And then this allows you to model, say, effects of voltage on liquid crystals, and so on. Okay, going into groups. So there are different types of groups that you can put in your simulation. I'll maybe talk about the more common ones. So structure group allows you to combine different complex geometries, or different geometry primitives together, like circles and rectangles and triangles together, and then put them in a single group to create a single geometry. And then analysis groups are very useful when it comes to do post-processing on your simulation results. So we will take a look at these when we look at maybe other examples. So the advantage of structure groups and analysis groups are that they are scriptable. So when you open up the property editor of a group, there's a setup script and then analysis portion. And then inside each of them, you can define your own parameters. So you can imagine that when you're designing something that you want to optimize, it's beneficial if you parameterize your design. And so this will allow you to define some variables. Let's say you're designing something and you can define the X span, Y span, and Z span of your design. And then in the scripting section, you can actually use our scripting language to create the geometry according to the variables that you have defined here. So this allows you to create complex geometries that are parameterized. So then when you do a parameter sweep, you can actually easily vary your design between simulations and then see the effect of the parameterization. So that's an example of the setup script. So here you can see that you can use Lumerical script to define or set up your simulation based on the parameters that you have defined. And then this is the analysis script. So the setup script portion allows you to set up your simulation. So either your geometry or your monitors and so on. Whereas the analysis portion allows you to do post-processing once the simulation is done. See, so again, you can define variables, and you can also define like the results that you want to collect after the post-processing. And then in the scripting section here, you can see that the script commands are called get data. So obviously this is used after the simulation has been run. So you have results available in your monitors and you want to do some post-processing automatically. And so these, you can use a script to collect results from those monitors and then do post-processing on them to get some results. And so the nice thing is that Fdtd and Mode both comes with an object library where there are lots of analysis groups available. And so you can, they're pre-loaded with these post-processing scripts that can allow you to do lots of calculations very easily without writing your own script. Okay, so now we are going into the solvers and the simulation objects that go with the solver. So when you're running an Fdtd simulation, as we just saw, you need to put a solver object in there because it will define like what is the 2D area that you're running a simulation with, or what is the 3D volume where you're running your simulation. Fdtd ports allow you to automatically inject light from one location and collect the light in another location, and allows you to calculate the optical S parameter for your device. The mesh override region is something that allows you to control the simulation mesh. So when you set up your simulation in Fdtd, depending on what material you have in your simulation volume, it automatically refines the mesh so that the mesh is fine enough everywhere to capture the propagation of light easily. However, in some cases, you may need to have more control over the mesh. And so these mesh override regions are objects that you can place in different places, locations of your simulation, and then make the mesh either finer or coarser as needed. So it gives you more control over the mesh. So here are some examples of the different boundary conditions that you can apply. See if I can move it again. So here we have an example of the metal boundary condition. So you can see a Gaussian beam light coming from the top. Sorry, maybe I need to. Right, sorry, the video started early. So here you can see that we have a perfect metal boundary at the top surface. And so as light goes to the boundary, you can see that it reflects 100%, and then there's no absorption on that top surface. So if you have a metal boundary condition in your simulation region, this is what you would use. Let's see. Okay. Now this one uses a periodic boundary condition on the sides here. So you can see that it's a plane wave that goes from the bottom up. And so if you have a plane wave, one thing to keep in mind is that on the sides, you always have to use a periodic boundary condition. And then here also you can see that the geometry that you're simulating has this periodic nature. So instead of simulating this whole big structure, what you can do is you can also simulate just one chunk of it. And then you use periodic boundary condition on the sides. And then that will allow you to simulate as if you're simulating the whole design. So we can see that here we are simulating 3 periods of the design, but it actually extends beyond it. And so by using the periodic boundary condition, you can actually limit the volume that you're simulating and run things faster. Okay, so this one is one of the most common boundary conditions, PML boundary conditions, perfectly matched layers. So the simulations that we're running here, these are all numerical simulations. So as light goes out of the simulation volume, in most cases, if you're assuming free space, you want the light to just simply go out of your simulation region, and you don't want any reflection coming from the simulation boundaries, which is actually pretty difficult when you're running simulations in a finite difference time domain approach. So the way things are done is that you add an extra material layer outside your simulation volume, and then you control the index of that material in such a way so that the light that goes from your simulation region to this external layer, you match the index in a way so that there's no reflection in the boundaries. And then at the same time, as light goes into this PML layer, it gets absorbed rapidly so that no light reaches the outer edge of your simulation and you get reflection from there. So PML is a very common boundary condition, and the different parameters that goes into defining a PML boundary condition, you can actually tweak them in Fdtd. However, like most of the cases, if you just use the standard definition of this boundary condition, it just works. So I'll run the video again. Here you can see you have a magnetic dipole source, a point source here. As light comes out of it, you can see that it reaches the boundary and then just goes, it looks like that it just goes through the boundary, where it actually is getting absorbed in the PML layer. And so light can just go out of your simulation volume. moving forward. So here are like some of the different types of PML boundary conditions that are available. So as I mentioned, like in most cases, you can just use the standard PML. When light goes on a PML boundary at a steep angle, in order to absorb the light completely within the layer, you actually have to make the PML layer thicker. And so again, kind of like without worrying about what goes into the details, if you know that you have light that are gonna go on very steep angles onto your PML boundary, you can just choose the steep angle boundary condition there. Sometimes having PML in your simulation can cause the simulation to diverge. And if you have a complex simulation with PML where you can see diverging behavior, the first thing to try would be to use a stabilized PML that often tends to resolve your diverging issues. So that's one option that you can use. And then the custom option is if you know a lot about PML boundary condition and you want to tweak the parameters yourself. So this is an advanced setting, and then this will allow you to choose the number of layers inside your PML layer, and then other different properties, the absorption coefficients of the layers and so on manually. Okay, so now we are into symmetric and anti-symmetric boundary conditions. So when you're running simulations on a geometry where you have symmetry, and so for example, here, I believe this example is just a free space. However, you can see that when we propagate light, a plane wave through this free space, you have to be careful about the electric field. So the way the electric field here is located, you can see light goes in the Z direction here, which is shown using the pink arrow. And then the electric field of the plane wave is shown with the blue arrow. And then you can see, depending on your plane of symmetry, you either have symmetry in your electric field or anti-symmetry in your electric field. So here you can see the EX goes in positive direction on the right half in your simulation, but negative direction in the left half of your simulation. So if you think about, or if you want to plot the electric field, you can imagine that it's positive on this half, while it's negative on the other half. And so if you want to use a symmetry boundary condition here, you have to use an anti-symmetric boundary condition. And then that way it will allow you to run simulation on half of your volume and run simulation faster. However, what happens is once you have run your simulation, Fdtd will automatically collect the data on this half of the simulation and unfold it and plot the result for the other half as well. So even if you're running your simulation for half the volume, when you look at the result, you'll actually see the result for the whole system. So in this example, I believe we are looking from the top here, and depending on the electric field, you can see that along this line, you have anti-symmetric behavior on the two sides. However, if you think about this other red line here, and you look from between the top portion and the bottom portion, which is more easily seen here, you can see that the electric field line is now perpendicular to the monitor here. And so both on the left and the right, you have electric field in the same direction. And so this is a symmetric behavior, and you use a symmetric boundary condition here. So in the perspective window, you can see that this is a 3D simulation. So it's a 3D volume, and you can actually break down your 3D volume into 4 quadrants. And if we use an anti-symmetric boundary along this vertical line here and a symmetric boundary along this horizontal line here, you can actually run a simulation in just a quarter of your volume and still get results for the whole geometry. And so that's what's shown here, is that even though you're running simulation on this quadrant here, you actually get the results for the whole volume. So in any simulation, wherever you have a geometry that has any symmetry, it's a very good idea to use the symmetric or anti-symmetric boundary condition so that you're running as small a simulation as possible. However, like when you look at the results, like it'll unfold the data automatically and give you the result for the whole volume. The only thing to be careful about is that when you're using a source like a plane wave, pay attention to the electric field direction, and then pick either anti-symmetric boundary or symmetric boundary, depending on the direction of your electric field and the plane of symmetry that you're using in your simulation. So symmetric and anti-symmetric boundary condition can also be used for periodic structures. So it doesn't have to be kind of like a standalone structure. Even if you have periodic structures, you can use symmetric and anti-symmetric boundary conditions. So one example here is that, let's say, if you have a structure where in the X and Y direction, your geometry is symmetric. Maybe you have a pattern of nanoparticles on the top surface of your solar cell, and you're trying to do a 3D simulation. You can just pick one particular unit cell in your volume, and then you can set the X and Y boundaries to be periodic. However, let's say if it's a solar cell, light is coming from the top surface and then it's going into the bottom. And then so you want the light to be absorbed after it reaches the bottom of your cell, right? So for the Z direction, you have to use PML boundary condition so that there are no artificial reflections coming from the top surface or the bottom surface. So that would be kind of like the typical settings for your boundary. However, if your unit cell itself is symmetric, then you can go one step further, and then let's say depending on your electric field of the plane wave, you have to use anti-symmetric boundary on the X boundaries, and then symmetric boundary on the Y boundaries. And then so this will allow you to actually run simulation even in a quarter of your unit cell, rather than running a simulation for the whole unit cell. So when you're running periodic boundary conditions, even then, you can consider if you can use symmetry within the unit cell and make the simulation volume even smaller.
Sir,
so next up is block boundary. Sorry?
May I interrupt, sir?
Yeah.
Sir, actually, there are some questions in the chat box. If you can answer them, it will be very helpful for us.
Okay, let me open up the chat box. Sorry, I haven't paid attention to this one. Okay, yeah. So I guess this is a very good question. I don't know if you can see the chat screen. Probably not. So as I'm looking at the questions, one of the question is that if you run Fdtd simulation, by default, it takes over all the cores of your computer. So that's not nice if you're running a simulation for a long time, because your PC may become unresponsive. So in that case, you can actually define like how many cores you want to use by Fdtd. So maybe I can open up Fdtd here. So this resources button allows you to set up your simulation resources. So I'll click on it. And then so here, you can actually set how many threads you want to use when you're running some simulations. Again, I have to apologize. Like I haven't used Fdtd in a while, and these settings have changed. However, there are very good documentations in our website, but just to kind of like give you an idea, this is where you set up how many threads you want to use when you're running a simulation and in what capacity. And if you look into the documentation, you'll find more details as to exactly what this means. The processes here is if you want to break up your simulation into different machines, this is where you can break it down. So a single simulation can be broken down in multiple processes. So this is like if you have a very big simulation that you cannot run in a single computer, you can add more resources here, and then point to the IP of the computer that are in the same local area network, and then you can run simulations, like break down your simulations into multiple machines as well. So any kind of like consideration about running simulations in different machines, or kind of like controlling how many threads or cores you want to use in your machine and keep like some of the other threads unoccupied, that's all done here. Right, and then I can see there was a question about getting access to the files. So as I mentioned, like usually these are shared beforehand so that during the workshop you have access to them. Given that like how you're doing the workshop now, I was a bit lazy and I didn't share them beforehand, but I'll share all of them with the organizers right after the workshop today, and then hopefully you can get access to them afterwards. Okay, and then there was another question about taking a break maybe around 9, so which will be in 10 minutes. So we can do that. So maybe we'll go for another 10 minutes and then have a quick break. Okay, so going forward with boundary conditions, the block boundary condition is very similar to the periodic boundary condition, but it is it gives you an extra added accuracy if you have light incident at an angle. So the difference between the periodic boundary condition and the block boundary condition is that it also keeps track of the phase as light goes out of one boundary and enters through another. And that can be inaccurate if you're using a periodic boundary condition with a non-normal incidence on the two periodic surfaces. So block boundary conditions can make your simulation run slower. So in a lot of cases, if you're running periodic boundary conditions with single frequency sources, a periodic boundary condition is enough. However, if you have a broadband simulation where light is getting injected at an angle and the phase is critical, then you often have to use block boundary conditions. Okay, so these are kind of like some of those details. Like the block boundary condition is more memory extensive, and then so in the Fdtd simulation object, when you're selecting boundary conditions, here you can select block boundary conditions, and then you can set the settings for the block boundary condition down here. Usually just keeping to the defaults works. So now it's kind of like an example of how the block boundary condition is different from the periodic boundary condition. So you can see that with the periodic boundary condition, as light kind of like was going through this surface and came back from this surface here, you could see that the angle was different. Whereas here, using block boundary condition, the light that escaped through this surface here, they came in at the same phase from this surface as well. So that's why when you have light coming in at non-normal angle in a periodic boundary condition, you want to use block. Okay, so now we are into different types of sources. So the most common one is a plane wave source. and this is something that you will be using in a lot of cases, I believe. So if you're using doing simulations for, let's say, solar cells, or if you have a surface, you want to shine light and then see how the light scatters from the surface because of nanoparticles or because of I guess like, yeah, metal particles, and then you want to see the plasmonic effects. In all of these cases, the source that you use is a plane wave source. And so the specialty of a plane wave source is that you have light from all different grid points coming in the same direction with the same phase. Now, one thing to keep in mind with the plane wave source is that since light is coming from everywhere with the same intensity, same phase, on the boundaries that are perpendicular to the propagation of light, let's say light is going from left to right here, on these top and bottom boundaries, you cannot use PML boundary conditions if you have a plane wave. As you can imagine that as light goes through, it cannot get absorbed on these boundaries because that will create some edge effects. And so whenever you're using plane waves, you should use it with periodic or block boundary conditions. So I'll go back maybe one step. So again, if this is your plane wave and light is going into your simulation like this, the simulation boundaries on the left and right, you cannot use PML there. You always have to use either periodic boundary conditions or block boundary conditions. And then there's also another boundary condition called total field scattered field that we will see that you can also use. Okay, so one thing to note is that if you're using a plane wave and you're doing a broadband simulation, that is the light that you're injecting is over a broad frequency spectrum, the angle of the incident light actually becomes a function of the frequency. So you get the most accurate angle of incidence at the center frequency, or the frequency that you're most interested with. But at the lower and upper extreme frequencies, you get slightly different angles. This variation for, I guess, like for smaller band simulations is not critical, and in most cases you can still ignore the error in your simulation and get away with it. However, if you're doing a very broadband simulation, then that may not be as accurate. So usually what you would do is, if you have a broadband simulation, one way to avoid this error is that you break down your simulation into different bands, smaller bands, and then you can still run your simulation with a plane wave source. And since you're kind of like reducing this spread here, and then maybe you have like one band that goes from here to here, another band that goes from here to here, and so on. So if you break down your entire spectrum into, I don't know, 5 different groups, you reduce the error coming from the variation in angle and still get accurate results. However, if you have to run a very broadband simulation with angled incidence of light, then the way to get accurate results is to use the BFAST broadband fixed angle source option. And this can be accessed from the plane wave source and the plane wave type. Instead of using block periodic, you have to choose BFAST here. So this one makes sure that at every frequency, the light gets injected at the same angle that you define here in the source. However, using BFAST is also increases the amount of resource that you need to run your simulation, as you need a very small time stepping in your simulation. So simulation would take longer to run. It does not support nonlinear materials. And as it mentions here, injection above critical angle is not possible. And it's numerically less stable than the standard Fdtd simulation. So the whole point of saying this is that BFAST can be a really great way of running very broadband simulations with angle incidence and make sure that you get the correct angle at all frequencies. However, running simulations with BFAST can be complex. So in most cases, the recommendation is that if you have a broadband simulation and you have angle incidence of light, consider breaking up your simulation into multiple simulations with smaller bands. And that way you can still run a normal simulation and get accurate results. If you have to run a single simulation with a very broadband spectrum, then you can use BFAST and then get accurate results that way. But there could be like some stability issues that you have to troubleshoot. Beam source is another common source that you use. So let's say you have light coming into your simulation, but given your structure, you cannot use a periodic boundary condition on the sides. In that case, like you can use a beam source, because the beam, as you can see, decays on the surfaces. So you can actually use a PML boundary condition on the sides. And you can use a focused beam of light here as your source in your simulation. Dipole sources gives you point sources in your simulation. So these are useful in simulations, I believe, when you're trying to simulate OLED or LEDs. And you want to see that how the light in your LED that's getting generated escapes the packaging. In those simulations, you can put dipoles in different locations of your device and then see how light generating at each location escapes, how efficiently it can escape your LED design. And the total field scattered field source is something that I was mentioning earlier, is that if you have to run a simulation with a plane wave source, but then you're simulating maybe how light interacts with a single particle, so you can't really use a periodic boundary condition on the sides. In that case, you can use a total field scattered field source. So the total field scattered field source is basically a plane wave source, but then it has a box that defines the extent of the source. So Fdtd does some background calculation to remove the source from outside this box. So you still inject a plane wave source inside here, but any point, grid point that falls outside this gray box, Fdtd does some calculation and removes the presence of the source from here. So outside this box, you would only see light that gets scattered from this particle and then gets reflected out into this simulation volume. And so that way, you can still use PML boundary condition everywhere and be able to use a plane wave type source in your simulation. So if we look at the video again, it'll probably be obvious that as light goes into, you can see that the source is not available outside this box, but the light that gets reflected from the particle, that can freely propagate into the entire simulation region. And then you can figure out like how much of the light is getting scattered and so on. The mode source is another common source. If in your simulation volume you have light coming in through a waveguide or an optical fiber, that means that the light is confined in a particular geometry, and maybe the light, like only the supported optical mode in the waveguide is coming through. And that's when the mode source is useful. And for advanced users, there's also an import source where you can just import any arbitrary electric field profile as your source, and then you can just inject that into your simulation. So one use case for this would be, let's say if you have a very long device that you're simulating in Fdtd, the device is so big that you just don't have the numerical resources available to run the whole simulation at once. In these cases, what you can do is in your propagation direction, maybe you break the simulation into multiple parts. You inject light from the beginning. Halfway into your geometry, you capture the electric field using a monitor. And then you run a second simulation where you use that information from the monitor as a source. You load that data into your import source, inject the light into the second half of your geometry, and then see how light propagates to the second half. So that would be kind of like a simple use case. But there are like other cases where sometimes you capture the light into one half of your simulation, you do some post-processing on top of it, and then you inject it into the second half of your simulation. So those are kind of like some cases where you need to use the import source. And then finally, in monitors, index monitor is one of the most common monitors. And the reason you use it is that it simply shows you the index in your simulation geometry. So it tells you whether you're actually simulating the right structure or not. In some advanced calculations, you sometimes need to know the index of the geometry for some post-processing. So that's where index monitors can come in handy as well. Movie monitors are definitely nice for creating presentations. As I'm going through the slides, you can see a lot of movies, and these were all created using the movie monitors. So movie monitors are just electric field profile monitors, but then they record the electric field profile as a function of time. And so that allows you to see how the electric field evolves as a function of time throughout your simulation volume. Time monitors record the electric field and magnetic field as a function of time. So as simulation progresses, you can see how the electric field is high at the beginning, and then as light slowly starts to go out of your simulation volume, you can see that the intensity of the electric field goes down and down. Frequency monitors are the most common ones, just because most of the times we are interested in looking at the frequency spectrum from our simulation, and then so that's where the frequency monitors come in. And then mode expansion monitors are if you're running simulations with waveguides, then you want to see like the light that's going through your simulation, how much of that light is part of your supported mode, how much of the light is in the fundamental mode of your waveguide, or in the TE mode or the TM mode in the waveguide. Like, so the mode expansion monitor allows you to see what fraction of the light is supported by each of these modes and break down them into different components. And then finally, Fdtd ports. So ports are something that you can put in your simulation to act both as source and a monitor. And so in your simulations, you can actually put multiple ports, and then with a single simulation, you are able to figure out the S parameter between, say, your input and your output. So ports are really handy if you're trying to figure out the S parameter for some particular optical components. And then that way you can set up the input and output of your simulation, run a single simulation, and get the S parameter out of your device. Okay, so I think those were the slides that I had for the simulation objects, and it's 9 o'clock, so we can maybe take a quick break, maybe a 5-minute break, and then we can all intervene in 5 minutes. So I think it's 9:05 right now, so we can get back together at 9:10. So yeah, I mean, take 5 minutes break, and then in the meantime, I'll check the questions that are here in the chat window, and then after 5 minutes, I can maybe give you an answer to those questions.
Okay, thank you everyone. Let's take a 5-minute break, and then we will again continue our session.
Okay, I'm back. So I hope we can get started again.
Yes, sir, we may start.
Okay, thanks. Yeah, I know that we have 1 more hour. Yeah, a lot of things to talk about. So let's see how much we can cover in the next 1 hour. Sorry, actually 1.5 hours, I guess. Let's see. Okay, so maybe
Sir,
I'll
could we,
address quickly. Yeah, sorry.
sir, could we start with the question and answer session, then again continue?
Yeah, of course, yeah. I was thinking that the same. Yeah, let's talk about the questions quickly. Maybe I see 2 questions here. One of them is what actually happens in CW norm? What are we normalizing with? Source spectrum? Can we get frequency response when our input source doesn't hold the frequency, and how does the source frequency range affect simulation? Yeah, so that's a good question. Yeah, sorry that I wasn't very clear when I was talking about all the impulse response and the normalization there. So the answer is yes. When you run FDTD simulation, you will notice that the CW norm is enabled by default. I believe it shows at the bottom of the window. And so that means that all the results that you get in the monitors, for example, the spectrum that you get as your output, these are all normalized by the source spectrum. So as you kind of like saw in those earlier slides, that in order to get the impulse response of your system, what you have to do is that you have to get the electric field after your simulation. And then if you divide that by your source spectrum, then what you end up with is the impulse response of your system. And so that's exactly what you get when you run an FDTD simulation. And so the normalization is done with the source spectrum. And then can we get frequency response when our input source doesn't hold that frequency? And the answer is yes. So you can run a simulation with that goes from, let's say, I don't know, 180 terahertz to 190 terahertz. But in your monitor, you can actually set it up to record 175 terahertz to 195 terahertz. So the monitor can actually be set up so that it records frequencies even beyond your input, and that's fine. And that's possible because the simulation that you're running is a time domain simulation, right? So when the simulation is actually happening and we are calculating the electric field and magnetic field as a function of time, there's no concept of frequency there. You're simply pushing a pulse into your geometry, and then you're recording what happens to the light in a certain location after a certain amount of time. And then you're doing a Fourier transform to figure out what is the spectrum of the light that you're capturing at the output. So in that sense, there's no limitation as to the frequency domain that you want to see in your result. You just have to perform a Fourier transform in a way so that you can see the amplitude of frequencies even beyond the range that your source was defined for. So the answer to that is yes. Another question that I have here is, many plasmonic structures are used as biosensors to detect virus, blood group, etc. By any chance, is there any option to run these kind of simulations to represent the biomolecule attachment to the cavity or structure? I believe the answer to this is also yes. I am not very familiar with simulation of biosensors, but I do know that FDTD is used or can be used to simulate biosensors. Maybe let's do this. I hope you can still see my screen. So I'll just go into our website. I believe there are some biosensor examples here. So for example, this one. Is this the right example? Maybe not. Okay, so this is not exactly an Fdtd example. It's a mode example, but the same theory applies for Fdtd. Right. So I believe like, yeah, here you have a typical waveguide, and then you have an analyte on top of the waveguide where it will interact with, I guess, like some biochemical material that comes into contact with the waveguide. And when it comes into contact with the waveguide, the property of the analyte changes. And so the way you simulate these type of structures in an optical simulation is that you have a layer of the material that interacts with your biomolecule, and you have to know when it interacts with that biomolecule, like how does the optical property of that material changes. And if you have that information, then what you can do is like you can run one simulation where the biomolecules are absent, and so that the optical property of this particular analyte layer has some value. And then you run another simulation where you assume that the analyte has interacted with some biomolecule, so its property has changed. And then you run another simulation to see what is the effect of the change in the behavior of this layer on the optical property of your waveguide. So that way you can run, say, 2 different simulations and then see how your circuit behaves, given that there's some there is some biomolecule present in the environment or not. And that in my understanding is one example on how you would simulate a biosensor. And then when you have like the optical behavior figured out, then you can bring these to, maybe your biosensor is connected to a photonic circuit, and then so you can bring those informations into interconnect and then run other simulations. So hope that helps. And as you saw, like there are other examples on when I searched for biosensor, the other examples popped up. So yeah, feel free to go here and take a look at the other examples and see if they're relevant as well. Okay, so going back to my slides. So I believe like the next set of slides is, I'm gonna just quickly talk about the application of Fdtd in doing simulations of components that are used in photonic integrated circuits. So this is an example of simulating a Y branch using Fdtd. And so a lot of you are probably familiar with these type of components. These are used in photonic integrated circuits. A Y branch is used when you want to split the light coming into the input into 2 different branches. And typically you would break them equally, so that half the light goes into one branch and then the other half goes into the other arm. And so design, you have to design these in a way so that there's like limited amount of loss, and then like exactly half light goes in one and then the other half goes into the other one. The way you make sure that is by calculating the S parameter for your device. And so when we looked at the ports in Fdtd, in these type of simulations, what you would do is you would set up your geometry in Fdtd. So you can see the 3D geometry here for your Y branch. And then you can see these gray boxes are ports. So you set up 3 ports in your simulation, and then you set them up on the 3 terminals here. And then you run Fdtd simulation. You use a mode source to inject the light into, well, the mode source is built into the port. So you simply inject light into one of the ports, and then you collect how much light, excuse me. You simply calculate how much light is arriving at those other ports. Sorry. And so as you figure out like how much of the incident light is getting collected in these other ports, it gives you the S parameter. And the advantage of using S parameters is that once you know the S parameter of your device, you can bring that into your circuit simulator in interconnect. And then this Y branch, you can see that in a photonic circuit, it's part of a bigger circuit. And so you can import the S parameter definition in interconnect and then create a compact model for your Y branch for circuit simulation. Okay, so this was supposed to be an hands-on demo, but unfortunately, again, I will kind of like open up the files and then show you how the simulation is set up and go through the flows. Let's see. So here you can see the geometry of your Y branch. So you can see that it's the name of the geometry says GDS layer. So this structure was actually part of a GDS file, which contained the layer information. So simply a polygon description of this particular layer. And then when you import this in Fdtd, what you do is the GDS file only contains information about this 2D layer, right? So just the pattern. And then so when you import this, you actually tell Fdtd okay, something is happening here. Why can't I select this? Okay. Okay, so that's working. Something weird is going on with my monitor. When I'm opening the edit window here, it's disappearing and going somewhere else. Okay, that's too bad. Okay, so what I wanted to show here, maybe I can just show it with the rectangle. So when you import the GDS, it goes into a structure group. And then in the structure group, you also have an edit window. So I'll maybe just drop a structure group here and then maybe I can show. Okay, so that one is disappearing as well. Okay, it's too bad. Let's see, let's try this one. Okay, so this one is opening up. So even when you're importing a 2D pattern in a structure group, that structure group will actually have information about the Z layer that you can enter here. And that's because the GDS is a 2D pattern, right? So you just know the XY coordinate of this polygon. But in the GDS file doesn't contain any information about the thickness of this layer. And so you will have to define like where to locate this layer in your simulation and what would be the thickness of that layer. So that's something that you provide here. Well, in the GDS layer. And then it'll give you a 3D geometry in the end. So pattern plus the Z thickness and location gives you the 3D geometry. And then so here you can see that we have this Y branch. And then the way you set up this simulation, because we want to get the S parameter for this guy, we have to set up these ports. So in Fdtd, you can click on the port buttons to create ports, and then you can add as many ports as you want. And then you can drag and drop these ports to place them in different locations. So here you can see that on this input, we have placed one port. And then on these two other arms, we have set up other ports. The way these ports work is that they can act both as source and monitors. And so inside each of these ports, you actually have a mode source. And then you also have a mode expansion monitor. So if you're trying to inject light through one of these ports, then the mode source kicks in. And then if I go into the properties of this one, hopefully it pops up here. Okay, that's good. And so first part would be the extent of the port. So since it's a mode source, you can figure out like how big of an area you want to calculate the optical mode, and so that will be this Y and Z span. Let me see if I can show you. Right, so let's see. So as you can see here, so this gray box kind of like defines a simulation, a 2D simulation region that you use to calculate the optical mode in this waveguide. And so that's what you define using these XY coordinates here. So this actually works as a mode source. And then if you go into the mode properties, you can calculate the modes supported by this waveguide, and then you can select which mode you want to use as your input. You can either choose to inject a single mode into the waveguide, or you can choose to select inject multiple modes as well. And then the way you can do it is you can click on the select mode button. It'll open up the mode solver here. You can see the geometry of the waveguide. That is part of the cross section of your mode source. And then you can select, you can calculate the modes supported by this waveguide here. So we are gonna calculate, like, say 20 trial modes that are supported by this waveguide, and then we click on calculate modes. It shows you what are the modes that are supported by the waveguides. So the first one, looking at the TE polarization fraction, you can see that this is the TE mode that is supported by this waveguide. And then that's the mode profile. The second one, you can see by looking at the TE polarization fraction that this is the TM mode supported by this waveguide. And so that's mode number 2. And so you can choose either the first mode, like this single mode, and inject that into your simulation as you're running your simulation. You can even select multiple modes and then choose to push multiple modes into your simulation. I'll just select cancel here for now. And then you can see that when the simulation was set up, we actually selected multiple modes. And so when you run this simulation, it'll actually inject both the TE and the TM mode into your simulation to figure out how the TE and TM mode propagates through this Y branch. So the other ports are similarly set up here. So you can see that we have set up another port here and one more port here. And then I believe there's a movie monitor that allows you to record like how light propagates through this structure as you run the simulation. And then when you imported the GDS, you imported just the silicon layer that defines your Y branch. However, like you have oxide claddings on top of the silicon layer, and then you have silicon dioxide as part of your substrate. And so these rectangle models that silicon dioxide on top and bottom of your Y branch. So if you go into the properties here, you'll see that the material is set to silicon dioxide. And then this mesh order number is very important. When you have multiple geometries in the object tree and things are overlapping with each other, you want to make sure that in the overlapped region, the right material is getting the upper hand, right? So in the overlapped region, you want one geometry to occupy that volume rather than the other. And the way you can do this is by using mesh order. So when you drag and drop any structure in your object tree, by default, they have a mesh order of 2. And the larger the number of value of mesh order, the lower priority something has in case things overlap. So here we set the mesh order for the rectangle to 5 because we want this one to have lower priority. And so by default, the silicon waveguide or silicon Y branch has a mesh order of 2. And so in this overlapped region where you have the rectangle, like the silicon dioxide rectangle and the silicon layer overlapping, it's the silicon layer that's gonna get the upper hand, and it's gonna occupy this volume here. And so that's how you can make sure that if you have overlapped geometries, you still get the final geometry that you want. The other way you can make sure that the right geometry is getting priority in case of overlaps is by ordering them in the object tree. So if you have multiple things with the same mesh order, then whatever comes lower in the tree gets preference over the ones that came at the top. So you can imagine that, like, if you don't worry about mesh order, you just keep adding structures in your tree one after another. As you add more and more geometries, the one that came at the bottom, like the last one, takes priority over the other ones. So that is another way to make sure that the right geometry is getting priority over other ones. And then we have a Dft monitor here. Let's see, just to get the electric field on the entire waveguide here. So that's the simulation setup. And then if you open up the material database, you can see all the materials that you have here. And then you will see that since we are using silicon dioxide and silicon in your simulation, you cannot delete them from the material database right now, just because they are getting used in the simulation. And when you're running a broadband simulation, it's always recommended to make sure that you go to the Material Explorer and make sure that the material model is selected carefully. So this is the Material Explorer. In the drop-down menu, you can select the materials that you're using in your simulation, or you can choose to show all materials, and then it'll just show everything from the material database. So the interesting material here is silicon. So let's select that, and then we can do a fit and plot. So you can see that the simulation wavelength here goes from 1.45 to 1.65 micron. So the dotted lines that you can see here are the imaginary part of the permittivity of silicon. So if I zoom out here also, you can see that that's the data. And so when you're running an Fdtd simulation, you actually have to fit whatever measurement data you have for a material with our multi-coefficient model. And so when you're running a simulation with such a narrow band, fitting is usually easier, right? Here you can see that the variation in the imaginary part is just it's basically 0 here for silicon. And then again here also you can see that there's very little variation in the band. But as you can see here, we are primarily interested in the mid wavelength, which is 1.55, a very common wavelength in communication. And so we are not worried about the fitting. But just to show you that if you're running a broadband simulation and you care about the fitting, then you have to make sure that this blue line, which is the actual model that gets used in Fdtd simulation, you want to make sure that it fits well with the data that you have in the model. And so in order to do that, first you have to set the wavelength range over which you want to have that good fit. So just for demonstrating that, let's set these to, say, 1, 2, 3 micron, and then see what we get. And then so the multi-coefficient model that gets used in Fdtd, you can control the number of coefficients and the fit tolerance on the left side here. And then that way you can make sure that you can ensure that you have a good fit. So with this new range, let's do fit and plot. And then so now you can see that since I have now a bigger range, the multi-coefficient model is trying to get a better fit with the data points. And so it is able to get a much better fit. The imaginary part is still 0, so we don't really care about that. But on the real part of the permittivity, now you can see that we get a much better fit. And then sometimes when you don't get a good fit, you can click on Show Advanced, and then there are like some other parameters that you can play with. One thing that I find useful is sometimes, given the source data, it might be difficult to get a good fit for both the real and imaginary part of the permittivity or index. In that case, sometimes you can put more weight on the imaginary part. So anything greater than 1 here will tell the fitting algorithm to give more emphasis on the imaginary fit. Anything less than 1 tells it to get a better fit on the real part. And then so that way you can kind of like change your priorities a little bit and get a better fit either on the imaginary part or on the real part, like which one is more important to you. In some cases, just to keep in mind, it might be hard to get a good fit, especially if you're running simulation over a very broad frequency or wavelength range. As you can imagine that if you look at this curve, it's very hard to fit this over the entire spectrum with a multi-coefficient model. In these cases, it's often recommended that you break down the simulation into into multiple simulations and then run simulations for a particular spectrum every time. And then that way you make the fitting more reasonable and more accurate as well. So once you have set up your geometry, your material, your ports, in this particular simulation, we are interested in calculating the S parameters for this Y branch. And then so what you can do is using this button, you can create an S parameter sweep. And S parameter sweeps only work with ports. So you have to first set up your ports. And then if you open up the S parameter sweep, you'll see that you have the option to excite all ports. So when you run this sweep, it'll inject light from all of the ports, one simulation at a time, and then calculate the light that gets captured into the other 2 ports. And then given that like we selected the T and TM mode for each of the ports, you can see that the table automatically shows you that for each of the ports, you have mode 1 and mode 2. So the 2 ports that you're exciting, and you're going to calculate the 2 modes at the outputs as well. Once you run the S parameter sweep and you have your results, you can export your results, save it in a particular format that can be opened up in interconnect, so that your Y branch can be made part of a bigger circuit by generating a compact model. And so this particular tab allows you to custom define kind of like the name of the ports. So when you're creating a compact model, maybe you don't call your ports port 1, port 2, port 3, but yeah, maybe you want to call them something else. Maybe you want to label your modes in some way. So you want to call them T and TM instead of mode 1 and mode 2. And then the mode ID is something that gets used in interconnect. So we will talk about these in the next day of the workshop when we talk about interconnect in more details. But these are unique IDs that interconnect uses to keep track of all the different modes. So 1 for TE and 2 for TM. That's what we're using here. And then so you can kind of like set up these in a way, and then you can choose to export the data into a text file that interconnect is able to read. Once the S parameter sweep is done, you can export the data in interconnect compatible format. You can also export it in touchstone format, which is a very standard format for recording S parameter data. Yeah, that's kind of like the simulation setup. I don't think running this makes sense right now, given that we don't have the time to allow this to run completely. So maybe I'll go back to my slides. And then let's see if we have some more information or results showing up here. Okay. Right, so once you run your simulation and you have the S parameter calculated, if you select one of the ports, like this is what the result view would show. So one thing that you get out of the ports is the S parameter. And then here, if you want to look at the S parameter for the Y branch, and then here we are plotting the absolute of the S parameter squared. So that would be the square of the transmission or the power that goes through. And then so you can see that on one of the output ports, that's the power that gets transmitted. So 0.36, 36% of the power is going from port 1 to port 2. So this is right now when you start with your simulation, it seems like that it's a pretty bad design because you're only getting 36% of your power in one of the output ports. And so that's where I believe like you want to now do an optimization of your design. So here, I think this design was parameterized, this particular example. And so you can perform, okay, no, so we're just doing an S parameter sweep here. And then once you run the S parameter sweep, as I mentioned, you can export the results to interconnect. And so this is how the text file looks like that gets loaded into interconnect. And it simply records the transmission from port 1 to port 2, port 1 to port 3, and so on, and records them as a function of frequency. So here you can see these are the frequency points in your simulation. That's the amplitude of the transmission, and then that's the phase of the transmission. It all gets saved in a text file in the format that interconnect asks for, and then you can just load it in interconnect. So in interconnect, you use an element called an S parameter element, and then you load the data that was saved from your Fdtd simulation, and then you end up with a compact model that you can use in your circuit. Okay. Let's see. Okay, let me check the time here quickly. So I believe we have 45 minutes. Okay, so maybe I'll stop the Fdtd part here, and then maybe I'll just quickly go into mode because I want to just introduce all the different solvers that are part of mode as well in the next maybe 45 minutes before we run out of time. So I'll just switch to mode right now. And then if we have more time, we can come back to Fdtd, or maybe we can have some time at the end if there are more questions. I'll just quickly check if there are more questions. I don't see any right now. So okay, so let's go ahead with the mode part. Okay, so today is all about our optical solvers. So we took a quick look at Fdtd and just got introduced to the different simulation objects and saw a couple of simple simulations as to how you set up your simulation. So now we will talk about mode. So Lumerical mode is designed to, I guess, like the primary focus is to run simulations on waveguides, but also on devices that has pretty long propagation distances. So Fdtd is a very powerful solver. However, like if you have a very long device and you have to do a 3D simulation, the simulations can get pretty large and time consuming, resource consuming. And then in a lot of cases, you can do some simplifications and maybe run a simulation on a cross section. For example, if you have a waveguide, all you need to do is run simulation on the cross section of the waveguide to see what sort of optical mode is supported in the waveguide. And that gives you all the necessary information rather than running a 3D simulation of the waveguide in Fdtd. Just because as light propagates through the waveguide, there's really no variation in the geometry there, right? So you can get away with a 2D simulation using an Eigenmode solver. So mode actually has 3 different solvers inside it that allows you to perform simulations on these type of devices. So the first one here that you see listed is called var Fdtd or variational Fdtd. I think it's the first one in the slide just because it is very similar to Fdtd. The only difference is that it's in essence a 2D Fdtd solver. So what you do in var Fdtd is that if you have a geometry where there's no variation in the vertical direction, so for example, the Y branch simulation that we just saw, on that one, the silicon layer has a particular thickness everywhere, right? So if you know what that thickness is, and you somehow incorporate the effect of that thickness in your simulation, by adjusting the index of the silicon layer, you can, in a sense, collapse your 3D simulation into a 2D simulation, where you just care about the pattern of your silicon layer, and then you inject light from one side, and then you see how light propagates through the to the Y branch. So you kind of like collapse your 3D simulation into a 2D, and then that way you don't have to run an expensive large 3D simulation, but you just run a 2D Fdtd simulation. And that is what you can do with the var Fdtd simulation. And then it allows you to run simulations of structures where they're typically planar structures, so the geometry in the vertical direction doesn't change, but you simply change the pattern on the 2D layer. And then that allows you to simulate big structures very quickly because it's a 2D Fdtd simulation in a sense. So this is kind of like shows you what I was just talking about. So you collapse a 3D waveguide slab into a set of 2D effective materials. So imagine this ring modulator where you have oxide cladding or oxide substrate everywhere, and then you have this silicon layer with a particular thickness, and the thickness is uniform. What you do is you look at the slab of the silicon and you calculate the slab mode into that silicon layer, and then the effective index of the slab mode becomes the index of the material as you convert this structure into a 2D structure. And everywhere you have silicon, you simply use the index of the slab mode as the index of the silicon material. And so that way you can run a 2D simulation, but by using the index of the slab mode instead of the effective index of the silicon layer, you also take into account of these multi-stacked layers that you have in your simulation. And so that allows you to get accurate results even though you're doing a 2D simulation of a 3D geometry. And so what type of designs can you run, simulate using var Fdtd? So a Y branch or an MMI, a ring resonator, these are valid examples because in the vertical direction, you can see that the thickness is uniform. However, like a taper like this or a grading coupler, where you have variations in the vertical direction as you propagate the light through the geometry, in these cases, a var Dtd solver is not valid because in the vertical direction, the definition of the device is not constant. So this is an example of a ring resonator. We just saw a video of that, I believe, a while ago. I'll just play it again. It's really nice to see. But so this is a good example of where you can do a var Dtd simulation. The ring resonator is a big structure here. So, and if you want to do a 3D Fdtd simulation, it will take a long time to run the simulation and a lot of resources. Using var Fdtd, since the waveguide geometry is a planar structure, has a certain thickness, you can calculate the slab mode. Well, var Fdtd will calculate the index of the slab mode for you, and then it'll automatically run a 2D Fdtd simulation instead of a 3D one. And here you can see some comparison of simulation results between Fdtd and var Fdtd. So right away, in terms of simulation time and memory usage, you can see that if you take a structure of this ring and then try to do a full 3D Fdtd simulation, so this particular structure was still reasonably small. Looking at the numbers here, I can see, but still, even this small ring took 338 megabyte of memory and then took 1500 seconds to run. Whereas with 2.5D var Fdtd, it took 18 megabyte of memory and 15 seconds to run. So the reason we call it 2.5D var Fdtd is because even though it's a 2D simulation, you take into account of the vertical direction by calculating the slab modes, and so it's more accurate than a simple or 2D simulation. And then so that's to indicate that the name says 2.5D var Fdtd. And so if you look at the simulation results though, the blue line is the spectrum of the ring resonator from 3D Fdtd simulation, and the blue line is from the VAR Fdtd simulation. And you can see that the simulation results from VAR Fdtd agrees very well with what you get from a full 3D Fdtd simulation. So given that there is a factor of 100 difference between the simulation time and a factor of, I say, almost 20 in terms of the memory usage, it's definitely a very good starting point to first design your ring in using VAR Fdtd. That way you can run quick simulations, optimize your design, and then once you have your final design, if you want very accurate results, you can always run a single 3D Fdtd simulation to get that very accurate result in the end. But when you're kind of like at the initial stage of your design and you're trying to do parameter sweep, you're trying to do optimization, it's definitely the better option to use VAR Fdtd. The other solver, and when you think about mode, this is probably the most common one that people uses, is FDE, or finite difference eigenmode solver. And so this solver is used to calculate the supported optical modes in waveguides or optical fibers. And so the way it works is it converts the 3D Maxwell's equation into 2D versions for a Z normal propagation. So you can imagine that the electric and magnetic field definition becomes a 2D representation of the electric field profile and magnetic field profile on the XY plane, let's say. And then you have this propagation term for optical propagation in the Z direction. And then light propagates through the Z direction with a particular angular frequency and a propagation constant. And when you define the Maxwell's equation in this way, and you want to characterize the optical properties of your waveguide in the propagation direction, you introduce a new term called an effective index, where the effective index of the waveguide is defined as dependent on the propagation constant of your optical mode, and can be calculated in this way. So when you're designing your waveguide or your optical fiber, you want to know how light is going to propagate through it, how the phase is going to change as light propagates through your waveguide or fiber, you want to know what is the effective index of the optical mode that is supported by that waveguide or that fiber. And so that's something that you can calculate using the FDE solver. And so obviously a very common use case is simulating waveguides. And then the things that you get out of an FDE simulation is, first of all, the optical mode. So whatever optical modes are supported by your waveguide, you can see the mode profile that allows you to know whether this particular optical mode is supported by the waveguide, or if you want to propagate light through the waveguide, whether it will go through the waveguide to a long distance, or it's just gonna dissipate and light will be lost. So the mode profile is something that's very useful and important, and then you can view your mode profiles using FDE. Group index, so which comes from the derivative of the effective index of your waveguide, and so you can perform a wavelength sweep or frequency sweep of your mode profile, calculate the effective index, and figure out the group index from there. And there are built-in tools that allows you to calculate the group index automatically. Again, you take another derivative and figure out the dispersion of light as light goes through your waveguide. You can calculate that too. Bending loss. So when light goes through your waveguide or your fiber, and then there's a bend, you can get optical loss coming from the bend, and it shifts your optical mode as well. So there are built-in tools that allows you to model bent waveguides in FDE. Coupling lengths. So for example, when you're simulating the ring, you can actually simulate the two waveguides that are side by side, and then figure out how light couples between the two modes on the waveguide and the ring, how they couple and over what length. These are some things that you can calculate. And then mode overlaps. So let's say you have a waveguide and then you want to couple the light from the waveguide into a fiber. And then so you can calculate the optical mode from the two waveguide and the fibers. And then there are built-in calculations to figure out like how does the mode overlap between the two, and then figure out like how much of the power you can actually expect to transfer from one structure into another. So you can do this type of calculations in Fde. So yeah, like I mentioned, like using those properties, you can simulate something like a ring resonator where, as you can see that the ring, the straight part of the ring resonator, the bus, is a straight waveguide. So obviously that's something that you can calculate with Fde and figure out like what is the optical mode inside that that bus. When it comes to the ring, you can see that it's a band waveguide. So you have to calculate the optical mode in the ring using the band waveguide analysis. You can define a band radius and then figure out how the effective index of this guy varies as you change the band radius. And then it also allows you to calculate the group index of the ring. And that's important because that defines what wavelength of light would couple with the ring depending on the radius. Okay, so I'm supposed to do a waveguide demo right now. So let's open up the simulation files. Okay. So here, this is Fde, and first thing you'll see that the design environment is very similar to Fdtd. So again, like we have your simulation objects at the top, the object tree here, and then if you look at the object tree and look at the geometry here, we have the substrate here, which is below the waveguide, and this should be oxide, as you can see in the material. And then we have the oxide cladding on top with another rectangle, again, oxide. And then here you can see the mesh order is 2, right? So that's why the waveguide, you can see that it's positioned lower in the object tree. So even though all of these have the same mesh order, because the waveguide comes after the cladding, in the overlapped area, it is the waveguide that's gonna win. And in your simulation, you're gonna see the waveguide. It's not gonna be overlapped, kind of like overshadowed by the oxide surrounding it. And then inside the waveguide, you have defined the geometry of your waveguide. You've set up the material to be silicon, and that's your setup. Now you put the simulation region, Fde, surrounding it. So in mode, as I mentioned, there are multiple solvers. So in the dropdown, you have your Eigenmode Solver, which is Fde, which is what we're going to use right now. There's the var Fdtd solver, and there's the other EME solver that we will talk about very soon. So here we've placed the Fde solver here. It's a 2D solver because you're solving the optical mode in the cross section of the waveguide. If I go into the property editor, you can see, you can figure out the orientation of the 2D structure. So here we just are running simulation on the XY plane. Go to the geometry that defines the simulation, the extent of your simulation region. So one thing to keep in mind here is that how big do you want to make this simulation region? When you're trying to run a simulation of a supported mode in your waveguide, most of the optical electric field are going to be confined inside the waveguide, but there's going to be still some electric field that remain on the surface. And the intensity of that electric field decays exponentially as you go farther and farther out of the waveguide. And as a rule of thumb, the electric field will drop by several orders of magnitude as you move away, at least half a wavelength away from your waveguide. So by default, when you set up your simulation region, you want to make the simulation region at least half a wavelength away from the outer surface of your waveguide, if not more. And then you can, of course, do some convergence testing. You can run some multiple simulations by making the simulation region bigger and bigger, and see if that affects your affects your result. But as a rule of thumb, as long as you're at least half a wavelength away, that usually should be okay. So that's your simulation region. Mesh setting, how fine a mesh you want here. So it's how finely you want to resolve the electric field inside the waveguide and outside the waveguide. And so the way you do that in mode is that you define how many grid points you want in the X direction and Y direction. That's the most common way. You can also define the stepping size and use that instead. And then boundary condition. Most commonly, 99% of the cases when you run an FD simulation and you want to calculate the optical mode, you would use a metal boundary condition on the surroundings, just because computationally it's really light and it's more stable. And so that is why it's more important to make sure that these boundaries are far away from the waveguide so that the electric field decays enough, because we are using metal boundary conditions on the surrounding. You can also use PML boundary conditions in cases where you have evanescence fields on your waveguide surface, and you want to see how those fields behave as light propagates through your waveguide. In those cases, you can choose to use PML boundary condition on the outside. So if you have a lossy waveguide and you want to figure out like how much light you lose as it propagates through the waveguide, in that case, you have to use a PML boundary condition, because then any light that escapes from your waveguide would enter the PML and get absorbed, and then that way you can model the loss coming from your waveguide. And then in the material section, usually, so one difference between FDE and Fdtd is that FDE is a frequency domain solver. You're calculating the eigenmode supported by your waveguide at a particular wavelength. And so since it's a single frequency simulation, there's no need for material fitting, ideally, right? You simply take the wave material index at the wavelength that you're running your simulation for, and that's it. However, if you want to calculate the group index of your waveguide, then you would have to run a frequency sweep or a wavelength sweep. And when you're doing a wavelength sweep, at that point, you want to have accurate variation in the index as a function of wavelength. And then it makes sense to use a multi-coefficient model. So that's why in the material section, you'll see that we are still asking the solver to fit materials with the multi-coefficient model, just like we did in Fdtd. And that's because you're not only going to run simulation at a single wavelength, but you would also, in most cases, want to do a wavelength sweep. And then you want the proper dispersive nature of the material. You want to capture that effect accurately. So the way you run an FD simulation is slightly different from what you do in Fdtd. This thing is. So once you have set everything up, you click run, and that actually opens up the Eigensolver analysis window. I'll maybe pop this one up. It's slightly bigger. And then in this one, you select at which frequency or wavelength you want to calculate the mode. So here by default, it's set to 1.5. So if we run the simulation now, calculation now, it'll calculate the optical mode at 1.5 micron. You set how many supported modes you want to find in your waveguide. And then you simply calculate the modes. As you run the simulation, it calculates all the supported modes in the waveguide. You can see the resolution here is really bad. That's because we have a very coarse mesh. If you want to fix that, you go back. Either you go into the Fdtd mesh settings, and then you increase the number of grid points here. So you can set the mesh cells to say 200 cells in X and Y directions. Say okay, run, and then calculate the modes again. Oh, sorry. I think I changed this setting here. So this one will be a little bit slower now because we have a finer mesh, but you can see now the electric field is resolved in a much better way. And you can see that with 99% T polarization fraction, this is the TE-like mode supported by the waveguide. And then the second one, it has a low T polarization fraction. So this is the TM mode supported by this waveguide. In most cases, when you're modeling a waveguide, you're interested in the fundamental modes, but you can see that it also calculates the any other supported and unsupported modes in your simulation region. So that simply tells you the effective index and then the loss in the system. So here we have a pure silicon waveguide at 1.5 micron where silicon is not absorbing at all. So you can see that the loss is 0. Now, if we want to calculate the group index, what we can do is we can do a frequency analysis. So we go here and then we can sweep the frequency or wavelength to figure out what is the group index. Okay, let me pop this one up again. So when you're doing a frequency sweep, you first have to do a single simulation at the frequency, at the starting frequency, let's say 1.5 micron. And then now I go for frequency analysis. And then starting from 1.5 micron, I can do a sweep up to 1.6 micron, maybe let's say 10 number of points. And then every time it'll calculate 8 modes. But then you only track one mode, the one that you have selected here. It'll keep track of that particular mode as it does the frequency analysis. And then you perform the frequency sweep here. So as you do the frequency sweep, it's calculating the optical mode for all the frequency points that I defined. So 10 different points. And then it's calculating the effective index for all those points. So this is going to take a few more seconds. And then once the simulation ends, it'll plot the effective index as a function of wavelength. You can see that the plot is getting updated here as the simulation is running. And then it'll also automatically do post-processing and figure out what is the group index of the waveguide based on the frequency data. And then it'll be part of the simulation result that you see. So you can see that that's how the effective index of the waveguide is varying as a function of wavelength. So you are capturing the dispersiveness of the waveguide. And then in terms of the plots, if you go to the frequency plot here, you can see that by default, you're looking at the effective index, but you can also look at the group index. And so that's how the group index is varying as a function of wavelength. Since we did multiple points, we can also look at the dispersion. And so you can get the dispersion as a function of wavelength. So all of these are important parameters when you're characterizing a waveguide. And so they're all calculated here. And then once you have characterized your waveguide, you can also export this data to generate a compact model of the waveguide in interconnect. So if you go to data export here, you have the option to export to interconnect. And so the effective index, group index, dispersion, the mode profile, all of this information will be saved in a Lumerical data file and that you can load into interconnect to create a compact model of the waveguide.
How did you go to that export data tab?
Oh, so it's here in the once you have done your frequency analysis. So by default, it's here in the set calculation parameters. But once you're done, you can then go to data export. And then, yeah, I think typically interconnect expects the data to be in LDF format, which is the Lumerical data file format. And if you do export to interconnect, it'll just allow you to save the file in an LDF file that you can load in interconnect. And then here, again, kind of like we'll talk about this in the next session, but you can define the orthogonal ID for the mode, and then you can label the mode. So let's say this was our T mode, and then ID of 1. Sometimes, as you're running these simulations, the loss that you get is the ideal loss, right? But if you do measurements on your waveguide in an actual, like once you do fabrication, there are loss coming from surface roughness that is not captured in this simulation. So there is an option here that you can override the loss. You can set this to true, and then that will allow you to, let's say, when you did measurements, you know that you get 200 dB per centimeter loss in your waveguide. You can just override that here, and then now if you say okay, it'll save the data for the waveguide in that LDF file that you can open up in interconnect later.
How did you get that menu? Can you show it again? I just missed
Yeah,
that
sure.
part.
So again, like when you go to data export, after you click export to interconnect, that opens up that menu, right? So you set up the file, you click save, and then it pops up that editor. Here you can kind of like set the mode label, orthogonal ID, and then if you want to give the loss from experimental measurements, like you can do that. So let's say this is a more lossy waveguide, so you do 300 dB per centimeter. And then once you say okay, if I go back to that folder here, you can see that test.ldf got generated, and then this is something that you can load up in interconnect. Okay, so let's see what's up next. Looking at the time, we have 15 more minutes. Okay, so let's go to EME. So the third solver that Mode offers is EME. And this is particularly useful when you have either very long devices where like in the propagation direction. And also like if you're trying to optimize a device where you want to say change the length of your device as an optimization parameter. And so if you're optimizing something very long with Fdtd running these long 3D simulations multiple times as you're optimizing, it can be very inefficient. In those cases, EME can be very helpful. So we will see some example cases. So the way the Eigenmode expansion solver works is you first divide your simulation geometry into multiple cross sections. And for each of those cross sections, you calculate the eigenmodes or the supported optical modes on each of those cross sections. You then figure out the overlap between those modes and the modes in the next segment of your geometry. And then that way you can figure out as light propagates from one cross section to another, how would they couple? And if light is going to be propagating nicely, or if you'll get some reflection, or if you'll get some loss as light couples from one cross section to another. So the nice thing about it is that once you have defined your geometry and all the cross sections, you first just calculate the supported modes in all of the cross section once, and then it's all post-processing, trying to figure out how the overlap works from one slice to another, and then you can figure out how light is going to propagate from one end to the other, and then you can change the distance between those cross sections and optimize your design without running any further simulations. Let's see. Right. So here is an example where you can simulate a taper using the EME solver. So the geometry of the taper, I don't know how legible this is. We will open up an example soon, and then you'll see. But here the taper has a particular thickness of the waveguide on one side and a narrower waveguide on the other side. And so the cross section of the waveguide varies from a much bigger waveguide to a narrower waveguide as light propagates through it. When you're designing a taper, you have to change the length of the taper to see how small a taper you can get away with and still not get a big loss in your design, right? So that's the challenge. And so the way you would use an EME solver to design your taper is that you will break your taper into different cross sections. So as the width of your waveguide changes, say you break it down into 20 different segments, you calculate the optical modes for each of those sections, and then you can calculate the overlap between the modes of each of the sections. And then with EME, you can change the distance between those sections, and then let's say you can easily calculate what would be the propagation of light if the overall length is 10 micron versus what will happen if the overall distance is 100 micron. You can see that the number of cross sections that we have here is same between this case and this case. It's just that you're spacing them further away from each other. So the nice thing is that you just calculate the number of modes in each of those cross sections at the beginning, and then you can simply change the distance between them and figure out how that affects the overall propagation of light from one end to another. And then that way optimize your taper design. And so as you sweep the taper length without doing any further simulation, you can see that as you make the taper longer and longer, the transmission goes up. And then for this particular design, you can see beyond 150 micron, the transmission is almost 1. So that kind of like tells you like where the sweet spot is. Maybe you want a transmission of 0.9, so you know that like maybe 100 micron long taper is enough. Now, if you want to do this optimization in Fdtd by running full 3D simulation and then like increasing the length of the taper and running a new simulation every single time, you can imagine that for this 11-point optimization, Fdtd takes more than 6 hours, EME takes less than 3 minutes. And given the structure we have here, that the light is confined in the waveguide, and then you can calculate the supported modes in the waveguides very accurately. The accuracy of the simulation is really good. So you can see that with full 3D Fdtd, you get the green dots, and that blue line is from EME, and the agreement is really good. So again, kind of like similar to VAR Fdtd, what you do in this type of device designs is that you start with EME, which allows you to find an optimized design very quickly. And then if you want very accurate results, you can then go to Fdtd, run a big 3D simulation, and then that gives you accurate result for your final geometry. Okay. Let's see. So this is another example of a simulation that you can do with EME. So this is a Bragg grating. And so here you can see that you have different grading orders, different gratings, and distributed in space. And so you can see the edge depth of the waveguide changes as light propagates through the structure. And you can define different cross sections on different regions, and then that way you calculate the supported modes on the different layers that have different edge depths. Again, like you can define a cell in EME in each of those locations, and then that way you can propagate light through the grating and then simulate the behavior. And the nice thing about using EME for this type of structures is that you can see you have, say, a full thickness of silicon in one region and then an etched silicon in another region. And it just kind of like follows periodically. And so you don't have to simulate the entire structure even. EME allows you to define periodicity. So you simply define two cells in this particular simulation and then use periodicity. And then you can define like how many periods you want to include in your simulation. And so you can see here, like you can just have 2 steps in your grading and then define a period of 500. And then that would be equivalent of simulating a Bragg grading with 500 periods. And then from the simulation, you can see that you can get the typical spectrum of your Bragg grading, where you get complete reflection within this band, but light transmits before and after that particular band that you're designing for. So again, simulating something like this with Fdtd is gonna be really difficult, just because you can see that the periodicity is in the propagation direction of light. So you cannot use periodic boundary condition in Fdtd. And so simulating such a structure the only, I guess, like reasonable approach would be by using EME. Okay, so we'll do a quick demo of a spot size converter. I believe we are in the last 10 minutes now. So this will show you how the simulation is set up using EME, which is a little bit different, or quite a bit different than the other tools. Let's see. I'll just make this bigger. Right. So the way the EME tool is set up is somewhat similar to Fdtd in terms that you have ports. So here you can see that we have our design here, and then we have one port here, and then another port here. And then between these ports, we have these cells. Let me see. How do I show the cells? Okay, I'll figure that out later. So the way the EME setup works is, as I mentioned, you have your geometry. Maybe I'll hide this one for now, just to show you the geometry first. Right, so you can see that we have a spot size converter here. So we have this silicon layer, and then we taper the silicon layer so that light couples out of the waveguide and goes into this bigger waveguide here. And so that's why when you go back to your simulation region, you have your port here where you would inject the light into your silicon waveguide, and then you have another port here where you would try to see how much of the light from the waveguide is coupled to the optical mode here. And then you set up your ports on two sides. So now what you would do is, as your silicon waveguide tapers out to a very thin width where it no longer supports any optical mode, so that light has to slowly couple out of the waveguide, you break down this entire length of the silicon waveguide into multiple segments, and then in each of the cells you calculate the optical modes. And so that's what you do in the EME setup here. So in the EME setup, you define where you want to start the calculation, which started at this -8 micron location, and then how many groups you want. So the first span that we have is the first segment where the waveguide length was constant. So that's a 3 micron length here. And then this is a constant width. And then there's another 3 micron segment at the very end after the taper ended. And then so this is where like we have everything constant again. And then in the middle, this middle group here is where the width of the waveguide is varying. And so here we have used 19 cells. And as the width changes from one cell to another, the width is continuously varying from one segment to another. And you use the CVCS option to make sure that you get a accurate calculation of the optical modes. It accounts for the variation of the width between the two adjacent cells this way. And then so the higher the number of cells that you use, the more accurate you will be. But yeah, I think like given that it's a gradual change in the thickness, you don't need a lot of cells. We have like 19 cells defined here. And then so what you do is when you're setting up your geometry, these the length of these group spans kind of like define where each of those cells are located. Let me see if I can, oh, display cells, there you go. So now if I do display cells and say, okay, now you can see the EME cells. So the first segment from 0 to 3 micron was here, and then the silicon waveguide was constant length here. From here to here, you have those 19 cells as the silicon waveguide tapers out. And then here also the waveguide is finished. And then so we have a constant region here again. And then so that's how the setup works. So yeah, you set up the cells. Again, number of mesh cells, because each of these cross section is effectively an Fdtd solver. You're calculating the optical modes supported by the waveguide in that area. And then so you can calculate the mesh setup for those Fdtd cells. We've kept this at 50 just to make the simulation run fast. You can use more a finer mesh if you want more accurate results. Boundary condition, again, like in each of the cross sections, these are Fdtd solvers, like Eigenmode solvers. So you use metal boundary condition in most cases. For material, again, we are doing a single frequency simulation, so we are not worried about using the multi-coefficient model here. So no need to worry about that for now, I guess. And so that's how you set up your EME setup. The geometry is set up in the same way. You just have to define the how many number of cells you want in the varying portion of your design. And then you run the simulation. So when you click run, the first thing it does, it just calculates the optical modes in each of those cross sections. So given that we have a very coarse mesh, calculation happens really fast. And then so once the calculation is done, it opens up the EME analysis window that you can see here. So at this point, we have calculated the optical mode on each of those cross sections. And so now we are ready to propagate the light. So that's where the EME propagate button comes. So when you click on this, the solver now will calculate the overlap between each of those cross sections and then figure out, like, if you inject light from one side, how much of it will arrive at the other part, and if there's going to be any reflection and so on. And so you calculate EME propagate, and then so now it does the calculation again with a very coarse mesh. I think it's really fast. So EME propagate is already done. And then so now, okay, yeah, I guess we're running out of time. And then so once you do EME propagate, you can see that the EME solver region now has the S matrix. And then so you open up the S matrix, and then you can see that's the S11, S22, S12, and S21. And then you can see that 0.5, that's the transmission value from port 1 to port 2, 0.505. So this is the amplitude of the transmission, not the power. So you can imagine that the power would be 0.505 squared. Right, so I guess 30% of the light. So let's see. And then so the nice thing about EME, the main thing that I wanted to show you is that in this particular simulation, the length of the taper region was 10 micron. But once you have calculated all the optical modes, and once you have calculated the overlaps, changing the length is as easy as doing a propagation sweep. And then we would want to change the span of the group number 2. And then we want to sweep from, say, 10 micron to 100 micron in, let's say, 10 points. And then we click on EME sweep. And then that's how fast you can calculate the S parameter by changing the length from 10 to 100 micron. And then now if you click on visualize EME sweep, you can calculate the S11, and then let's see if we want to plot the absolute square. You can see that that's how the optical propagation varies. Let's see, S11, don't want S22. And so that's how the optical S parameter varies as you change the length of the taper region. So you can pick how big you want to make the taper in order to make sure that the light propagates through it nicely. Okay, so I think we've run out of time. So let's see if there are any more questions. Okay, so sorry, we ran out of time. I wasn't very careful about checking my watch. So yeah, I guess like there's one question showing like how to create an account and download the examples from our website. Maybe I can just quickly show that. So as you go into Lumerical website, you can see that there's a sign in button. If you click on that, it takes you there. And then if you don't like, I have an account, but if you don't have that account, then you can click on register now. And then when you do that, then you can use your BUET email address or your university email address. So it has to be institute email address. It cannot be like a generic email address like Gmail or Yahoo Mail. But you can use that to register. And then once you register, then you can use that to log in. Okay, it's gonna take me to my, yeah, it's gonna take me to my employee portal. So I don't want to do that right now. But once you have logged in, then all of these examples are open to you.
They actually want us to register for support of some of the examples. They show that error.
Oh, okay, okay. Yes, that's a good question. Register for support. I think you can actually do that from within the tool, but I myself have not done that. So I think like one easy way to do that would be if you go to the forum. I don't know if you're aware of the forum that we have. If you go to our forum, then you can also search for question answers there. Or let me try this. Okay. I guess like, yeah, as I mentioned, I have not done this myself before. So what I can do is I can maybe forward the information to the organizers, and then they can maybe forward this to everyone. I think there is definitely a link that you can use to do support registration. I just can't seem to find it. Yeah, sorry about that. I think like, yeah, I'm sure like there's a link that can take you to support registration. So I'll share that with everyone maybe afterwards. Okay, sorry, I think we ran out of time and I have a meeting right now. So
Thank you,
hopefully we
sir.
can